get started.
All right, we are Team Fight and Flight, and this is our response aerial firefighting aircraft, the hydroplane. These are the team members. And these are design requirements. We were given a request for proposal. Some of the important requirements were we wanted it at entry into service at 2030. We wanted to use an existing engine or one that would be in development by 2028. The required fire retardant capacity was 4,000 gallons, and an optional objective was 8,000 gallons, with a multi-drop capability with a minimum of 2,000 gallons per drop. We wanted a design radius of 200 nautical miles and an optional objective of 400 nautical miles, with a ferry range of a required 2,000 nautical miles and an optional objective of 3,000 nautical miles, an adapt speed required of 300 knots and an optional requirement of 400 knots. Some of the implications for the request was we decided to go for the objectives and goals instead of the design requirements, and this decision was made so that if the objectives could not be reached, we would still be able to fit the requirements. We chose a load factor of 5 because of the importance of low altitude maneuverability during firefighting missions. We wanted our aircraft to be reliable in case of smoke ingestion during firefighting missions, and we added a ground tracking radar, which would be useful in heavy smoke.
The mission profiles were created in order to estimate the takeoff weight for the design. The purpose of the ferry mission here was to relocate the aircraft to the area of the fire. The different segments it includes are shown in the figure: takeoff, climb, cruise, loiter, descent, and land. The aerial firefighting mission is shown here. It was divided into the segments: takeoff, climb, cruise, descend, loiter, drop, another climb, cruise, loiter, descend, and land. However, it was simplified for the weight estimation because the method did not allow for payload drops. So to initially estimate the takeoff weight for the design, we considered the weight of the crew, the payload, the fuel required for the mission, and an empty aircraft weight. We used an iterative method to solve for the gross takeoff weight for each segment of the mission profiles previously seen. To accomplish this, data from military and cargo bomber aircraft were used to estimate empty weight fractions, and loss of fuel after each mission segment was considered. This iterative equation we used is shown here, and results were obtained for both jet and turboprop configurations. And then
is it my internet problem or?
No, we think one of our members.
where did I leave off?
We got just basically the configuration, so I think just quickly go over the numbers, then we'll move on.
I think Olivia is having technical difficulties. One moment.
Let's move on to the next section, then we can come back and get this or answer questions about it at the end because we have limited time.
Yeah, we can go ahead and move on then.
Okay, moving on.
The aircraft wing design began with first finding the wing loading for the aircraft. We desired the aircraft to be 100 knot stall at sea level to meet the 125 knot optional requirement for deployment speed. So we figured 100 knots gives a 25 knot factor of safety. Additionally, we wanted flaps on the aircraft, and so we, using this graph here on the right, we chose a CL of 2.2, use that to backsolve for our wing loading. From there, we could design the aircraft wing. After knowing the wing loading, and that would help us figure out our planform area, next we needed to determine our airfoil, And so we performed a trade study involving multiple different airfoils where we examined the maximum lift drag, or L over D, the angle of attack where max L over D took place, coefficient of drag at L over D, and the maximum coefficient of lift at stall. We evaluated all these at a Reynolds number of 3 × 10⁷, and we found that the FX6300-100 airfoil performed the best. The wing geometry was then developed after the airfoil was chosen to focus on optimizing L over D at cruise. We added sweep, incidence, and dihedral for various reasons, mostly stability and to improve and optimize the lift to drag ratio in cruise. Additionally, a mid-wing layout is chosen for the stability considerations and to help reduce structural weight. And then the table on the right here just has a quick summary of the wing geometry. Most importantly, it just has a reference area of 1861.74 square feet, and it has a 3-degree dihedral with a root chord of 17.3. To help increase the wing's performance, we gave it winglets. The winglets were designed in XFOR5, where we just varied several different parameters until we were happy. The wingspan was, the winglet is 7.5 feet with a taper ratio of 0.24, and it's canted 50 degrees from the horizontal. After that, again, we wanted flaps. And so we performed an analysis, and we found that our wing produced a coefficient lift of 2.0 roughly. And we desired a CL of about 2.7 or higher. And so to meet this, we went with some slotted flaps, and the reference area of the flaps to the wing is 70%. So these are pretty big flaps. And just the table on the right has various flap geometry considerations or parameters. After this, we performed a structural analysis. Analysis was mostly focused on the mechanics of materials approach with a trade study performed for the material. The trade study for the material found that the ribs should be made of 2024 T4, while the wings spars should be composed of 7075 T6 aluminum due to the greater amount of fatigue that the spars can take over the ribs. Mechanics of material approach, again, was used to size the main spar, which is an I-beam. And we varied through various heights, widths, and thicknesses to meet the minimum weight with a 1.5 factor of safety. Additionally, as stated earlier, we wanted a load factor of 5 with a focus on crew survivability, so that pilots could quickly maneuver in the valleys of California or wherever they may be. So on the right, we just have various parameters of what the spars ended up being. Again, we have a primary. We also have a torsional spar in the back that runs just along the flap hinge. And here we have a description of the spar. And it's important to note that part of the torsional load is also going to be carried by a carbon fiber skin. So this wing is going to be really strong in torsion. Additionally, wing ribs are modeled as being airfoil shaped I-beams with flanges 2 inches wide and a shear web of 1/8 inch.
So from our initial sizing, we determined that a turboprop engine would be the best source of propulsion for our airplane. Also from the initial sizing, we determined that our power requirement would be 20,000 horsepower. So knowing this, we did a trade study with a bunch of different turboprop engines, and among the considerations that we made were fuel efficiency and power matching. So in other words, how close the power supplied by those engines met our requirement. Even though it wasn't the most efficient engine, the engine that we opted with was the Pratt & Whitney 150. It perfectly matched our power requirement, so we ended up going with that one. We'll be using 4 of them on our airplane, 2 on each wing, and with those engines, we will be using a 6-blade Dowdy R408 type propeller, and those will also have a 13.5-foot diameter. For our fuel system, we opted to go with discrete fuel tanks. Those fuel tanks offer the best resistance to leaks. And so since we're a firefighting aircraft and we'll be flying over forest fires, fuel leaks could be very dangerous and disruptive to the efforts trying to put out those fires. So we made that a priority. Our fuel tanks will be able to carry 610 cubic feet, and that will be split between the wing tank and the fuselage tank, with the wing tank carrying a slight majority at 317 cubic feet and the fuselage carrying the remaining 293. We decided to go with Jet A fuel, and that fuel at that volume would weigh about 23,600 pounds. And this picture just kind of shows the layout. You can see in the blue represents our tanks. You can see that there's a wing tank mounted through the fuselage in the wing box. And on top of that is the fuselage tank that is mounted on the ceiling of the fuselage. We wanted to keep a space between them so that maintenance workers could routinely check and inspect the aircraft.
So our crew station consists of a pilot and co-pilot station, flight engineer station, a lavatory, and some extra equipment. We designed our crew station around accommodating the 95th percentile pilot, which is a pilot from around 65 to 73 inches. And some things we had to consider were the pilot's range of vision and providing plenty of room for our avionics and equipment. So you can see here a side view of our pilot and co-pilot station. This station has two pilot seats next to each other with a control panel in front of them. We were able to achieve an over nose viewing angle of 13 degrees, a looking upward viewing angle of 43 degrees, a grazing angle of 36 degrees, and over the side angle of 42 degrees, achieving all the recommended viewing angles for a commercial aircraft. Here's our flight engineer station from the side. The seat is exactly the same as the pilot and co-pilot, so it will accommodate the 95th percentile pilot as well. And this station is positioned right behind the pilot's seat, facing out the left wing. We decided to include a lavatory. Here's a rough model of it. This is for longer flights, for example, the ferry mission that's required in our request for proposal, just to make the crew a little more comfortable. This lavatory is located directly next to the flight engineer station, also facing out the left window when you walk into it. Here's a layout of our crew station. You can see the pilot and co-pilot station in the front, the flight engineer station behind those, and then the lavatory directly behind the flight engineer station. So some additional avionics and equipment we decided to include were, if you look on the front, on the left side of the screen on the front of the aircraft, there's an AN/APQ-187 military grade terrain following radar. This radar can provide ground info and low level flight when there's smoke in front of the windshield. It can operate at speeds of 5 to 300 knots and altitudes from 100 to 1,000 feet during both straight and turning flight. We decided to include this for the firefighting mission because the pilot will have to get closer to the ground and his view could potentially be obstructed by smoke. If you look to the right of that, there's a portable oxygen tank. This is for higher altitude flight when supplementary oxygen might be necessary for the crew. And if you look all the way to the right, there's our APU. It's a Honeywell 131-9A. It's used in many commercial Airbus and Boeing aircraft, and it can provide 115 volts at 400 hertz in order to provide power for all of our equipment.
So our initial fuselage design came from like just what existing cargo, like military cargo aircrafts have. We knew that we wanted a fuselage that was long enough for a far back tail to help stability. And we know we wanted a fuselage that was about 14 feet wide to accommodate our fire retardant tanks, our payload. And so, looking at, the similarly sized aircraft that are 14 feet wide, we got an initial fuselage length of 106 feet long. And then this was changed over time. So we figured out the main landing gear needed fairings on the side to accommodate, to house them. And then we also redesigned our initial nose to accommodate the crew station. Next slide. Or someone have that. So yeah, you can see here the fuselage. It's pretty typical cargo aircraft. And so for the fire retardant drop mechanism, the way it works is we have 8 tanks of 1,000 gallons each, and they're separated into 2 sets of 4 tanks. Or if someone could switch to, sorry. Yeah, there's 2 sets of 4 tanks of 1,000 gallons each, and they're on either side of the main landing gear. And so they have a single pipe that connects to a loading port above the tanks, so they can all be loaded simultaneously from the ground. And they can also all be dropped simultaneously because there's patches on the bottom of each tank that open independently of the other ones. So the way that the drop works is, well, we have 2,000 gallon standard drops. And so the way that works is 1 tank is picked from each set, like that are equal distance from the main landing gear to not move the aircraft center of gravity when the drop is made. And so all the retardant from those 2 tanks are dumped from the doors at the bottom, and the drop time is 1 second for a tank. So the drop time for 2 tanks is also 1 second. So if you go to the next slide, you can see the mechanism there. Yeah, and the pipe system for loading it and where they are on the aircraft.
Okay, so for landing gear, I start off with a picture of the top view of the landing gear and nose gear, and then a picture of the side view of the nose gear and landing gear. And then you can see that a tricycle landing gear was configuration is chosen, and this was because of its stability and mechanical simplicity. Additionally, a tricycle landing gear configuration allows the aircraft to fly at larger angles of attack during takeoff and landing. The main gear it consists of 2 independent retractable struts, and each are located 4 feet behind the aircraft COG, and nose gear consists of a single retractable strut located 29.3 feet ahead of the aircraft COG. And then on the next slide, you see the top view and the side view again, and this is the landing gear and nose gear being retracted. And then on the next slide, you see the main gear, and you can see pictures of the main gear, and we decided to go with 2 wheels on each strut. And the main gear we designed it to take 88% of the weight of the aircraft. And then on the next page, we have nose gear pictures, and the nose gear also has 2 wheels on its strut, and it was designed to take 12% of the weight of the aircraft. And then these are the Oleo shock parameters that we used as we designed our strut to be Oleo. And as you can see, there's the variables that we used and the description and the values we use. And then on the next slide, we actually have the landing gear Oleo shock parameters for our struts. And you can see the load on the mains is 8,025 pounds, and the load on the nose is 21,850 pounds. And the compressed air pressure and shock absorber is 1,800 PSI. And then for wheel sizing, the left side has the max static load nose, minimum static load nose, and the dynamic braking load nose equations. And then the figure below it shows the distances. And on the right side, we have the rolling radius and the wheel to weight and area. And on the next slide, we have the nose gear wheel sizing. So the model of the wheel that we went with was a Goodyear Aviation 31 by 9.75 14, and then the size of it was a 31 inch times 9.75 inch. And then the maximum load needed was 20,400 pounds, and the individual tire load was 11,000 pounds. And then on the next slide, we have the landing gear wheel sizing. And yeah, we have the Goodyear Aviation H43.5 by 16, and then that's the size of the wheel. And then the max individual tire load is 40,600 pounds.
So for designing the tail, we initially considered 3 different configurations. We looked at a conventional tail, a V-tail, and an H-tail. And all three were initially sized and compared so that we could select the best performing one. And we sized each tail using the tail volume coefficient method, which relates the area of the horizontal and vertical stabilizers using the wing geometry and pre-selected coefficients. For horizontal surfaces, we used a coefficient of 1, and vertical surfaces, we used a coefficient of 0.09 as suggested for jet transport aircraft. After sizing all three tails, they were compared for dynamic lateral stability in XFLR5. A root locus plot was generated with green representing the H tail, red representing the conventional tail, and pink representing the V tail. As you can see in the plot, the H tail displays the best Dutch roll stability with similar spiral convergence to the other tails. Because of that advantage in Dutch roll stability, the H tail was ultimately selected for our aircraft. This table lists all the dimensions of our aircraft, of the tail used on the aircraft, just converted for total feet as opposed to fractions of chord and span. This is just a 3D model showing the fully assembled H tail with the horizontal stabilizer in green and the vertical stabilizers in gray. For sizing the ailerons, we used historical guidelines. The limiting factor for us was the amount of wing left between the flaps and the winglets. So that ratio of wingspan was 0.289, and based on the historical guidelines, the corresponding chord ratio was 0.335, and the aileron was sized accordingly. For elevator sizing, we also used historical guidelines. If you look at the table on the left, we selected the jet transport to most closely approximate our aircraft. And so because of that, we chose a chord ratio of 0.25. And we selected the span of the elevator to be the entire span of the horizontal stabilizer, and that allows us to fully take advantage of the end plate effect given by the horizontal tail. And we also decided to place the hinge line of the elevator at 10% of elevator chord, giving us an aerodynamic overhang balance. This just reduces the torque load necessary to deflect the elevator. Rudder sizing initially followed the same process as the elevator, where we used the ratio of 0.32, also assuming a jet transport aircraft. However, after some analyses in AVL, we decided it was best to create stabilators on the vertical stabilizer. So the entire surface is moving except for the static part where it joins to the horizontal stabilizer. And doing this allows us to achieve zero side slip in engine out trim scenarios.
Static stability was evaluated using XFLR5 and EVL, so Athena Vortex Lattice, and both of them use a Vortex Lattice method solution. The XFLR5 can do viscous solutions, but it can't account for the fuselage very well, while EVL can account for the fuselage, but it just uses an inviscid solution and a constant zero lift drag coefficient. And the airplane is statically stable longitudinally, laterally, and directionally, with the longitudinal stability ranging from -0.28 to -2.3. And then you can see the lateral directional stabilities as well, but they're all acceptable. And then the airplane is longitudinally stable past the stalling lift attack. So in case of stall, it will nose down, which is good for safety. And here you can see the vortex spacing used in the AVL model. So the wing and tail are modeled using a bunch of different little horseshoe vortices, and then the fuselage, each of these sections represents a source plus doublet vortex. So this is sort of how the model looks, the way we did it. Dynamic stability analysis was also done in XFLR5 and AVL. So there's the entire process, but basically we just took some data from XFLR5 and then some hand calculations, and then inputted all of that back into XFLR5 as well as AVL, and they agreed well, especially for small angles of attack and side slip. And the airplane is dynamically stable in Dutch roll and dynamically stable spirally, and then obviously it's roll convergent. And it has a stable short period mode. However, because it has such a high lift to drag ratio of about 31 during cruise, the phugoid mode is slowly divergent for smaller angles of attack. And here you can see the longitudinal stability root plot. So you have the short period mode, which is convergent, and then the phugoid mode, which is very slowly divergent. And here you can see the lateral stability root plot. So all of them are convergent. Trim conditions were evaluated using AVL because Explore 5 doesn't work very well when you're trying to evaluate wide ranges of control surface deflection. But all angles of attack were well below stall, so the invested prediction should still be fairly valid. And the trim is possible up to 10 degrees angle of attack in the most statically stable pitch, which is fine because we don't need to be able to fly at more than about 8.4 degrees angle of attack for our takeoff, and also for our landing, we can land at relatively low angles of attack. And then you can trim up to 16 degrees, which is still below stall, even in the least statically stable pitch configuration. And the best lift to drag ratio is achieved when the airplane is at approximately 0 degrees angle of attack. So that gives us a cruise for a firefighting mission of 311 knots and a cruise speed for the ferry mission averaging at 205 knots. And then the airplane can fly with any 2 engines out. So that means that 1 engine out potentially allows the airplane to continue the mission, and a 2nd engine out necessitates diversion to the nearest airport to land. And it can actually fly and trim with only 1 engine out, but it can't trim at 0 side slip angle and has very limited excess power. So it should not be done. And to remain spirally stable, because we didn't want to increase the size of the vertical stabilizers, we ended up using all moving vertical stabilizers, as Christian already mentioned, because that lets us trim at 0 degrees side slip. And then for crosswind landing, because we have so much rudder authority, it's pretty easy to trim for crosswind landing.
So we then evaluated the performance and costs of the aircraft designed. First, we have the operating envelope, and we developed one for both the firefighting mission and the ferry mission with true airspeed in knots on the x-axis and altitude in feet on the y-axis. The dashed line shows the stall limit of the aircraft, the maximum dynamic pressure, which is where the structural damage will start to occur to the aircraft. If it passes this limit, that's the curve in orange. And the solid curve is where the specific excess power is equal to 0. So all the power generated from the engines goes into propelling the aircraft. And so these are the 2 operating envelopes. The next thing we checked was the propeller tip speed against the speed of sound. We account for the static tip speed and the speed of the aircraft at trim. And we account for that with the helical tip speed. We want to be not close to the speed of sound, so we compared against 85%. And we just want to make sure that we don't have that loss of efficiency that is associated with exceeding that limit. So we checked it for each stage of the flight, and we were below for each case. After this, we checked the range for both missions using the equation presented at the bottom left, which depends on specific fuel consumption, lift over drag at the flight section, and crucially the weight fraction. And we did this for both the firefighting and the ferry mission. We come to ferry range of 4,856 nautical miles and a firefighting range of 1,126 nautical miles. So both exceed the project requirements. We use a 1.1 factor of safety for weights in this estimate. After this, we estimated balanced field length using an equation presented by Raymer, which is typical of aircraft design. We use the characteristics of the aircraft, and we come to a balanced field length of 1,949 feet, meaning in the event of 1 engine out while the pilot's trying to take off, he can either complete the takeoff or brake to a stop in this distance. So after this, we estimated costs using the development and procurement costs of aircraft model. These are the parameters that are input into the model. Crucially here, we have production run of 25. So that's what the solution shows. On the next slide, we implement this. The equation is at the top. We run each of the numbers and the associated costs are listed, but we come to a unit cost of 230 million for this for a 25 production run. If we wanted to be closer to a comparable aircraft like C-130, we would need to reach $83 million unit cost, which we would need a production run of 500. So it's important to break into global markets to do this.
And that's everything. Do you want us to go back and go over the sizing stuff? If Olivia, you have your technical issues sorted.
Yeah.
Yeah, I'm not sure where I left off.
think you'd gotten through sort of the process, and then you're just going to talk about like what the fractions were and how each of the individual fractions worked.
Okay, I think I got through. So the equation we used is presented there, and then we obtain results for both jet and propeller configurations, since at this stage we hadn't selected one. And then this last plot here shows to evaluate the sensitivity of the initial weight to lift to drag ratio. We chose a range of maximum lift to drag ratios ranging from 5 through 50. And we calculated results here on this plot. I think that's all I was going to say.
Okay, thank you for the presentation. Let's ask our sponsors if they have any question.
Yeah, hey, this is Joel Ligeti from Northrop Grumman. Can you hear me?
Yeah.
Okay.
Yes, sir.
So I thought this was a good overall design, and I'm sure your aircraft is great. During a design presentation, you have to kind of show your work, and a lot of the slides were more about what the specs of the airplane were, rather than here are the requirements, here's the considerations, here's the trade, and this is where our aircraft, how we designed it and why we made certain kinds of trades. And I thought a lot of that was missing, because I'll see, for instance, the equation written on a slide, but then I won't see, in this case it was good, the one that's on the slide that's on right there, because it shows the actual chosen lift to drag ratio on there. But in some of the charts, it just showed the guidance, but didn't show where your actual chosen system was. So I think that's just an overall thing. It also helps, well, let me pause there and see if there's any comments.
No, you go ahead.
Okay, it also helps the reviewers if you have slide numbers. And I think there are some other slides that were in the presentation that basically what we call action captions. You would just say things like, let's see, cruise station layout. Rather than our cruise station layout was focused on the optimization of comfort versus functionality or something like that. So if you get to a point where you are just stating, hey, here's the thing that's on the slide, you should actually go, and I just realized I didn't have the video here. You should be a little more persuading or motivating on your slide of why and what you're showing to the reviewer, because what the reviewer has to do is judge the goodness of your design, and we can't do that if what you said was, here's the layout. Well, what considerations did you have? What driving factors did you have? All those kinds of things are good for us to know, because we weren't in the trenches with you as you came up with the design, but it's good to know that you considered this, this, and this. And that's how we do our job as a reviewer. Yeah, I have some detailed things which I can send to you guys, but other than that, that was basically the thing. I'm sure your plane is fine and everything meets the requirements. I just wasn't in most cases able to judge the goodness of your design.
Thank you. Do you have any other comments?
I know.
Okay, thank you. Thank you very much for your comments. I think I agree with him. And for this slide specifically, it's Olivia made this slide. So were you in the class when I talk about the presentation and the slides and how to make slide, how to make presentation? Were you in the class?
Yeah.
So you were in the class? Okay.
On Zoom.
You were on Zoom. Okay. So this is the thing I emphasize a lot for the students who in the class. You probably remember I said I emphasize a lot. Don't make the slides too busy. I mean, let me show it here. What? why the sharing stopped.
When you said, let me show you, I thought you were going to try and pull something up yourself, but sorry,
So
sharing again.
can you see here? The one I draw.
Yes, ma'am.
Yeah. So for this part, it's like you have so many words here. So what do you expect the audience? Do you want us to read or do you want to listen to you? If we read, we cannot listen to you. If we listen to you, we cannot read. Is this just too much information on one slide? You have a table, you have equation, you have a graph, and this much. It's very overwhelming. And a lot of our audience, we are, I don't know. For me, I started in the presentation from Monday morning, and everybody is in a fatigue mode now. And if you give me this much information and expect me to read, it's, I don't know. I personally do not prefer this kind of slides. It's very ineffective communication between you and the audience. And for the other things, I think for the amount of work you guys have done, and I think it's an amazing job. You did a lot of detailed analysis on everything and everything. I think most topics are done in a very professional way. Just make sure that if, let's say, we have 4 groups in our class, you need to justify why your design is good. Same comment as our sponsor just said. So that is very important. If you want to make your design stand out of 4 groups, this is not competition, but it's good that you can pay more attention on that. On the page, there's no page number, but when design airfoil selection. Let me erase this part. I mean, on this one, same thing. The thing on the right side, well, I can see the green, red, and the thing on the right side. Does anybody can really read?
Yeah, that was my bad. I was trying to scramble and find a good graphic. Unfortunately, this is the best graphic we had for airfoil selections.
Yeah.
Without recreating it, and we didn't have the time to recreate it.
Yeah, so I know that you guys are busy and just screenshot whatever from the software or anything. If something that is not readable, it is not necessary to put on the slide, because if cannot, okay, this is much easier to read, but I guess this is not same. It's a lift to drag ratio. It's the same graph? No, it's not. Yeah, try to make sure that everything you put on slides, we can get the information. And also the one you select is FX63100. What color represent the one you selected?
That was red on the initial slide.
Red on the initial slide, okay. So I don't see much difference of there's a red and a green. They're almost overlap. So what is, how do you justify that you think the red is the best? You see that the red and the green, they are.
So this is just one of our graphics of one. This is examining our coefficient of lift over coefficient of drag at various alpha. And this is just one of the 4 parameters that we ended up taking a look at to examine the best airfoils. I just figured a graphic would be an interesting thing to put on the slide. And trying to put all 4 graphics on the same slide would have been too much. They would have just occupied all the space, as well as they would have been even harder to read.
Yeah, I know. But
So,
in terms of presentation, I mean, if you want to persuade the audience that this airfoil is the best, you need to show something that really persuasive. So I know that we have like a lift coefficient in terms of angle tech and everything, and you have like moment coefficient and everything, and you probably combine all the information, and in the end you make the conclusion that okay, this one is the best. But purely from the one you showed here, I feel like I cannot understand why this one is best. So you probably want to give more persuasive information. If they, right, because right now from the graph you show here, okay, there is a red curve, there is a green curve, they're almost overlapped. I mean, if this one cannot prove this, the red curve is the best, change other proof, change to other thing that can prove that your selection is the best.
Roger that.
Yeah.
So I probably should have shown the table then.
The airfoil with the red curve, the 63-100, and the green curve, which was the FX63-110, also did score very, very similarly. The primary reason we chose the FX63-100 is that the FX63-110, there were a lot of problems getting it to the numerical solution with it to converge, and also the 63-100 did score very slightly better.
Okay. So make sure that in the presentation you need to emphasize the advantage of your selection to persuade the audience. And I think overall great job, because I feel like every topic was presented in a very logical way. You put like the engine selection, you put a requirement there. That is exactly what I want to see. A lot of the group didn't do that. And then you start use that one as a guideline to the design. And for the I don't have too much to comment on. I think your group did very well. And in terms of slides and the presentation, I think all the other topics that made the slides very clean and very comfortable to read. So really great job. And really appreciate that you guys did the dynamic stability analysis, even that is not required in this class. So this is kind of like extra work you have done in this class. And I